Hello and welcome to this webcast dedicated to SQL Server In-Memory OLTP. My name is Artemiou and I'm a Microsoft Data Platform MVP. In this webcast we're going to talk about In-Memory OLTP in SQL Server. This is the agenda of the webcast. So first we're going to see what exactly is In-Memory OLTP, the availability of in-memory OLTP in different SQL Server versions and editions. We're going to talk about memory optimized tables as well as natively compiled store procedures. And of course, we're going to see a few live demos in order to better realize how easy it is to get performance benefits using in-memory OLTP in SQL Server. So first, let's talk about what exactly in-memory OLTP is. In-memory OLTP, which stands for In-Memory Online Transaction Processing, is Microsoft's latest in-memory processing technology. As the name implies, it is optimized for online transactional processing workload. It can be characterized as a non-blocking multi-version optimistic concurrency control system. It features memory optimized tables, durable and non-durable, and natively compiled store procedures. Alongside that, it also features memory optimized table variables, etc. Let's see a diagram in order to better understand how in-memory OLTP is built into SQL Server's database engine. As you can see on the right on your screen, you have the traditional interpreted T-SQL query execution module accessing disk-based tables with indexes and so on. What was added with in-memory OLTP, it is a query interop module that allows you to access both disk-based tables and memory optimized tables as well. So you can have T-SQL code combining the access on disk-based and memory optimized tables as well. Furthermore, there is a new module for natively compiled store procedures, which uses an in-memory OLTP compiler. And every natively compiled store procedure, it is compiled at the time of creation into a DLL. And this DLL, when you call your store procedure, the process invokes the respective DLL, which can access the memory optimized tables and indexes. What you need to take into consideration is that with natively compiled store procedures, you can access only memory optimized tables and other memory optimized data structures, such as memory optimized table variables. On the contrary, with using the query interop, you can access both disk-based and memory optimized tables. But of course, in this scenario, you cannot use natively compiled store procedures. Now, regarding the availability of in-memory OLTP, in-memory OLTP was first shipped with SQL Server 2014, and it is available only in the evaluation, developer, and enterprise editions. The good news is that in SQL Server 2016 SP1 or later, in-memory OLTP is available in more editions, and specifically, it is available in the evaluation edition, developer edition, enterprise, standard, web, and express editions. So it's a fact that with SQL Server 2016 SP1 or later, special features like in-memory OLTP and much more are more affordable and thus easily accessible. So let's talk about memory optimized tables. Rows in memory optimized tables are read from and written to memory. So the entire table resides in memory. As said in the beginning, the records of these tables are accessed using a non-blocking multi-version optimistic concurrency control. So yes, there are no latches. There are two types of memory optimized tables, durable and non-durable. Durable memory optimized tables have a second copy maintained on disk for durability, and that means that in the case you have a failover or you restart SQL Server, this second copy on disk is used for reconstructing the memory optimized table in memory again. So you have no data loss when you use durable memory optimized tables. Of course, if you don't want durability and let's say you just use a table for ETL and you use it just for processing data and you do not want to store any data there permanently, you can use non-durable memory optimized tables. The last point about memory optimized tables is that via the query interop we showed earlier in the previous diagram, they are interoperable with disk-based tables. Of course, if you use natively compiled store procedure, you can only access memory optimized tables, as we're going to see later. So this is an example of two definitions of memory optimized tables. In the first example here, you can see how you create a durable memory optimized table. It is exactly the same syntax like creating normal disk-based tables, but you need to add the type of index, in this case non-clustered hash, and specify the bucket count. The bucket count represents the number of unique records in your index. So the recommendation is to use 1.5 or 2 times the number of records in the table. And with these two special keywords, that with memory optimized set to on and the durability setting, in this case we specify schema and data, we can create a durable memory optimized tables. Similarly, with only changing the durability to schema only, we create a non-durable memory optimized table. Now, natively compiled store procedures are compiled to native code, that is DLL, upon their creation. As you all know, disk-based store procedures, interpreted store procedures, are compiled at first execution. This is a huge difference when it comes to performance. At the compile time of the natively compiled store procedures, there are some aggressive optimizations taking place. Another point to take into consideration is that natively compiled store procedures can interact only with memory optimized tables and memory optimized table variables. And the call to a natively compiled store procedure is actually a call to its DLL entry point, which is something extremely fast when compared to disk-based store procedures. This is an example of a definition of a natively compiled store procedure. It has similarities to disk-based store procedures, but we add with some keywords, for example, with native compilation, schema binding. It is an atomic execution batch, and so on. Okay, enough with the theory. Let's see some demos using SQL Server 2016 SP1. Okay, for these demos I'm going to use some code I prepared. So the first demo features running multiple times insert statements. So we're going to try and simulate a high data insert rate. The first step is to create a database and make it In-Memory OLTP enabled. So I'm going to create the database In-Memory OLTP DB. I'm going to add a file group that contains that will be containing memory optimized data. I need to specify a location for this file group's file. So at this point you need to ensure that the directory you are using it is already created on your disk. For example, you can see I have memoptim data directory created on my C drive. And the last step is to set the isolation level for memory optimized table to snapshot. Great. Now, the next step is to create the memory, these demos tables. So I'm going to create 3 tables. I'm going to create a disk-based table. Then I'm going to create 2 memory optimized tables. Why 2 memory optimized tables? Well, the one memory optimized table will be used in using query interop, and the other one will be accessed directly from a natively compiled stop procedure. So I'm simulating a basic table with some person information. For example, ID, first name, last name, and the remarks column. As you can see, the structure is the same for all tables. As you can see, the durability for my memory optimized tables is set to schema and data, meaning that all memory optimized tables are durable. So in a case of failover or similar situation, there will be known data loss. I'm doing this in order to compare exactly the same things. I mean, to compare apples with apples. Okay, so you have your disk-based table, which is by nature durable, and both memory optimized tables are durable as well. Okay, tables are now created. I'm going to create as well the native compile store procedure. So this is my native compile store procedure where I specify the logic here, which the logic is to insert data into the memory optimized table created for this purpose. Now my natively compiled store procedure is compiled and ready for execution. Okay. Now it's time to execute this demos scenario. I'm going to delete the data, any data, from the demos tables. Sorry for that. Just to be on the safe side. Okay. And let me show you the scenario. As you can see, I'm running 200,000 inserts against each table. So I'm going to insert some sample values for 200,000 times on each table. This is the disk-based execution. This is the memory optimized execution with the query interop. And this is the execution using the natively compiled store procedure. For each mode of execution, I'm counting the elapsed time in order to compare it at the end. And of course, I have some queries in the end for just checking out that I have the same number of data inserted in each table. Okay, so let's execute the scenario. Great. As you can see, all three tables have 200,000 records inserted. Now, about disk-based execution took 2,740 milliseconds to execute. Memory optimized execution took 1,000 milliseconds. And memory optimized with natively compiled stored procedure execution took only 174 milliseconds. Now let's plot these results on a graph just to get a visual representation of the performance benefit in this simple demo. So, disk-based 2,740. Memory optimized 1,000 milliseconds. And natively compiled stored procedure 174 milliseconds. So as you can see from the graphs, we had for memory optimized execution a speed up of 2.74 times faster, and for the memory optimized with natively compiled stored procedure execution, we had an amazing speed up of 15.75 times faster than the disk-based execution, which is of course amazing. You can imagine what happens if you run this for even larger amounts of data. For example, perform millions of insert statements in real time, so on, what the performance benefits can be. Okay, let's proceed to demo 2 now. In demo 2, we are going to update the tables created in the first demo. So what we have 3 tables with 200,000 records each, and we are going to run a simple update statement against these 3 tables. More specifically, we are going to update the remarks column for each record in each table. So what I need to create for demo 2 is just a natively compiled stored procedure for running the update, and the 2 other update operations against the disk-based table and the first memory optimized table will be performed using the TSQL script. Now I'm creating the store procedure. So the natively compiled store procedure has been created. Okay, next step is to execute the scenario for this demo. First, let's check the contents of the 3 tables, top 5 records from each table. As you can see, it has some sample data, and if you know, the remarks column has the word remarks inside. We are going to update this column in each table. Okay. I'm going to run simple update statements for the disk-based and the first memory optimized table, and for the third one, I'm just going to call the natively compiled store procedure created earlier, passing as a parameter the new remarks. In the end, I'm going to check again the top 5 records from each table in order to show you that they were indeed updated. And here we go. Great. Now first let's check the contents. As you can see, the remarks column has been successfully updated on all three tables. Now let's check the times. So for the disk-based execution, it needed 1404 milliseconds. For the memory optimized interop execution, it required 214 milliseconds, and for the memory optimized execution with the natively compiled store procedure, just needed 143 milliseconds. Let's plot these results on the second graph in order to see a visual representation. So disk-based 1404, memory optimized 214 milliseconds, and 143 for natively compiled store procedure. As you can see in the graphs, the memory optimized interop execution had a speed up of 6.56 times faster than disk-based, and memory optimized with natively compiled store procedure execution gave the amazing speed up of 9.82 times faster than disk-based execution. As you can see from the demos as well, they were just some simple demos to illustrate basic performance benefit. You can run more sophisticated examples and see the performance benefits for your own workload. So In-Memory OLTP in SQL Server is extremely powerful. It is built into SQL Server's database engine, so it is easy to be used. It is easy to migrate workloads in order to make use of this technology and thus boost performance. Of course, always you need to perform a full analysis on your workload prior to doing any migration, and of course, prior to anything, perform extensive testing. Now, In-Memory OLTP is available in all major editions of SQL Server 2016 SP1 or later, and yeah, start using it today. Before closing this webcast, I'm going to show you a tool I have created for testing In-Memory OLTP. This tool is called In-Memory OLTP Simulator, and what it does is that it allows you to simulate workloads against SQL Server's In-Memory OLTP. So you get the tool, you connect to a SQL Server version and edition that supports In-Memory OLTP. This tool provides some standard scenarios you can use and customize the number of records in order to do some basic testing, but the Ultimate Edition of the tool allows you to create custom scenarios, and this is the power of this tool. It allows you to create scenarios that can easily allow you to test your own workload against the powerful In-Memory OLTP engine SQL Server. Just to show you an example of using In-Memory OLTP Simulator, I'm going to run a standard scenario that is updating a single column in a table with 200,000 records. So the first step is to initialize the scenario. At this point, In-Memory OLTP Simulator connects to the SQL Server engine and creates the required data structures for running the scenario's logic. That is creating the tables, natively compiled store procedure, populating the tables with the initial sample data, and so on. Note that during this phase, for any reason, you can select an emergency action, and that is you can stop the simulation, drop the scenario, drop all the scenarios from the database, and so on. Okay, now the scenario has been initialized, and I can proceed and run the disk-spaced mode. The first step is in every mode's execution is to clear the buffers in order to equally compare every execution. Disk-based execution has been completed. Now I proceed to run the memory optimized execution mode. And the last, the memory optimized execution mode with natively compiled store procedure call. Okay, these are the statistics. We had a speed up of 1.51 times faster than disk-based for the memory optimized execution, and 2.64 times faster from the disk-based execution. If you like, you can click on View Simulation Statistics and get more statistics about the scenario executions and so on. You note that you can run each scenario multiple times. You can compare these runs. You can view the fastest run, slowest. You can get an average, and so on. And of course, you can export these statistics in using a set of methods. Okay, last, some resources about In-Memory OLTP. You can visit the In-Memory OLTP library on MSDN. It has a rich set of articles on the subject. My official website and my blog. On my blog, you can find a large number of articles dedicated to In-Memory OLTP, and last but not least, In-Memory OLTP Simulator. You can download the community edition. It's free for everyone, and you can start testing out SQL servers in In-Memory OLTP. Thank you very much for watching this webcast. Until next time, take care.